Hello, and once again, welcome to the sixth lecture on thermodynamics for beginners.
Good morning, sir.
Good morning,
Happy
everyone.
Teachers. Happy
Happy
Teachers
Teachers
Day.
Day. God bless you all. And happy Teachers Day to all who are watching or will be watching, as I find that many guys are watching after this live streaming program. And therefore, since it is a very important topic, concept based topic, so I thought of making a video, lively video. So make it as lively as possible by asking me questions, interacting me in maybe in English or may not be in English, maybe in Odia. I will interpret that in English for the understanding of those who cannot understand Odia. I will interpret that. Don't worry. So far, let me share my screen and start today's proceedings. Um, are you able to see my screen?
Yes, sir.
Yes, sir.
This problem I have given to you, right?
Yes, sir.
Have you done
This
that?
one?
Yes,
Sir,
sir.
This you have these two problems you are supposed to do. For, forgotten, Mr. Rudra?
sir, not these two.
That
Sir, you have
too.
given different one.
Okay, that too. Omkar, is it not?
Sir, sir, these two I have done.
That means I have given, right?
Yes, sir. Yesterday you told you will do one and another one to do at home.
Sir,
Yeah.
these two one you have given in last class.
No, I have told, possibly you have forgotten that. This is a cyclic system, a, this question based on a cyclic process. And this one is simple. This one is a simple determination of del U, del S, del surrounding. So, so let us, for the sake of revision, you and for the benefit of those who are watching, let us try to revise in 10-15 minutes by solving problems. This is based on both first law as well as second law. You are going to find both internal energy change as well as the entropy change. For a process, 1 mole of monoatomic gas at 300 K in a 10-liter piston-fitted cylinder is allowed to expand to 20 liter in two different ways, adiabatically, reversibly. Have we done this problem in class or no? No, right?
No, sir.
Sir, I think you have done this.
The similar type, adiabatically, reversibly against a constant pressure. I think similar type we have done.
Yes, sir. Similar type. Yes, sir. Similar type question.
Maybe
So it was diatomic ideal gas. State one, state two, state three.
where it is. So, okay, you tell me how to proceed. First is a reversible process. or first irreversible. Let's see. Irreversible, you have to find out the temperature by equating two expressions. What are the two expressions that you have to equate, Omkar?
Sir, in reversible or irreversible?
Irreversible.
The irreversible delta U is equal to W.
That is true. That is for all.
You say it's coming minus
Oh,
what?
I'm not saying minus. What two expressions you have to equate? Rudra?
Sir, minus P delta V and NCP delta T.
Yes. N?
In R delta T.
Eh?
So, uh, sir,
And what?
CP.
Eh? What?
This CP.
Eh?
Sir, NCV delta T. That is inter.
Yes. Because del U is never related to Cp. Del H is related to Cp. Del U is related to, that is the, you know, uh, dQV by dt is equal to Cv. So du is Cv dt, and if you integrate, then del U will be equal to Cv delta T. Got it?
Yes, sir.
Then why you fumbled for two times? NR, once you told NR, then NCP. So, and this is irreversible. This is for both.
Yes, sir.
So, when you are taking up irreversible first, this one first, the second one first, then you have to, since the external pressure is given, so you can use this expression, and the volume change is also given. So you can use this expression to find the work done is equal to minus 0.5 atm into V2 minus V1, 20 minus 10. It became how much?
The 506.5 joule.
Minus 5 liter atmosphere, right?
Yes,
And if you multiply with 101.3, it becomes joule. How much?
minus 506.5.
So this is the work done, expansion work done, which is negative in our convention, and Q, as you know, there is no need to tell repeating that in adiabatic process there is no heat exchange. Whatever work done, you know, is converted to change in internal energy. So that is why del U is equal to W, and that also, you know, in this particular case, W is a state function. Particularly adiabatic work done is path independent. इसको हम लेना पड़ेगा. ओके, इसको हम निकाल लेंगे. Okay, then we have found out del U for the irreversible process, and you have to find out the delta S system. So tell me what expression you have to use for del S system. There is no need for using this Cp delta T to find temperature because it is not asking to what temperature it will fall, it will drop down. There is no requirement in this question. So del U we have already done. And then we find out del S, what expression. But if in any case, you have to know the temperature, right?
Yes, sir.
So in both the expression, general expressions that we have, tell me one of them involving V2, V1, Rudra,
Uh,
tell
s-
us.
Sir, NCB ln T2 upon T1 plus NR ln B2 upon B1.
Yes. So on the second one,
Sir, NCP ln T2 upon T1 minus NR ln P2 upon P1.
well, yes. Okay. But which one you want to fit in here for this question? The first one or the second one?
Sir, the first one.
Okay. Since the volume data is given, so it is better to use the first one. But in any case, you have to find the final temperature. So that you have to use this expression that minus 500 6.5 is equal to 1 mole CV. The data is not given since it is monoatomic gas. It is 3.3 by 2, 8.3 into delta T. The final temperature is not known. This T2 minus 300. So from here we can find T2. Can you find this for me? Welcome those who are watching directly from the YouTube live streaming source. Welcome.
So one,
Sir, 259.31.
Yes, Omkar, what you are saying?
sir, I in the reversal when I used V1 gamma minus when I only came 189 Kelvin.
No, 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 no. That is reversible. I am not talking of reversible. I'm talking of irreversible. I told you that adiabatic gas laws are applicable only for the reversible process, ideal process. The irreversible processes are not ideal. For that, you have to find out the final temperature by equating NCV delta T, which is universally applied for any process, and this exclusive expression that we use for irreversible process is minus P external into delta V. You got it?
Yes, sir.
So what is the final temperature? You just calculate once again for me,
Sir,
Mr. Omkar Nath. Yes.
sir, 259.31.
So let's take 259.3 Kelvin. So definitely it is correct. It is appearing to be a correct calculation because there will be cooling effect in adiabatic expansion from 300 to 259.3. Here is a question for you, Sami, if you can answer. In the case of a reversible expansion to the same volume, is the final temperature greater than 259.3 or will be lower than 259.3? Sami, will you try? This is irreversible
Sir, can you
expansion.
repeat the question?
Yes, I am repeating the
Sir, can you
question.
repeat?
When, yeah, you, uh, this we are taking irreversible expansion from 10 liter to 20 liter, and we found the initial temperature was 300 K, and now the temperature has been reduced to 259.3 K. Had the expansion, adiabatic expansion been reversible, a slow process, then what would have been the temperature? The final temperature would have been lower than this or would have been higher than this? Yes. Okay. Rudra,
Sir, it will be higher.
Omkar,
Sir, in reversible, it will be lower, sir. The final temperature.
precisely Omkar is correct. Uh, because the work done during expansion, the work done is more, and in reversible, which is a curve, maybe it is lying lower than the isothermal curve, but it is a curve. The area is more, but in expansion, the external pressure is the final pressure, which is much lower. So the small rectangle, that area is much smaller than this area. So since the work done in reversible process is greater, so it will spend more of its internal energy, and therefore the temperature will be lowered to a greater extent than what it would be if the expansion would be done suddenly against a constant pressure of lower value. I hope you understand. Do you?
Sir, can you please repeat?
Your microphone is not working. I am not able to hear you properly. So can you somehow fix up your microphone? Maybe you are away from microphone, or something is. Can you repeat your question? Yes, Sami.
No, sir, I was asking if you could repeat.
So tell that with I mean, microphone audio cannot be volume controlled. I don't know, but I can hear Rudra's voice loud and clear, but I'm not able to hear Omkar and Sami's voice loud and clear, very faint. So where is the defect? The defect lies with me or with you both. Try to fix it if possible. Now, what I said, I have told several times, and I'm really surprised when Rudra said the temperature will be more. I was really surprised. I think it was a slip of your tongue, right? Or you could not recollect that. What happened? Rudra, what happened?
Sir, I misinterpreted the question.
Now, when Sami and others who are watching, I really feel very sad to repeat this again and again. This is PV graph. Your starting point is here. You are carrying out an expansion isothermally, and reversibly it will be here. This is a isothermal, which we are not doing here. We are doing adiabatic, and reversible will be below up to this volume. So this is say 10 liter, this is 20 liter. This is adia, and this is isothermal. We are not interested in isothermal. And same adiabatic, but under a constant external pressure of 0.5. So in expansion, the constant external pressure is the final pressure which you will come. So we use this minus P external into delta V. So this area is much smaller than the area bound by this graph. So the work done in this is reversible, this is irreversible. The work done in reversible expansion is much greater than the work done in irreversible expansion. Therefore, as you know, in case of the adiabatic process, this is sorry, this is 0. So del U is equal to W. So whatever work has been done by the system, it is by expending, by spending its own internal energy. So the internal energy will drop, the temperature will drop. The drop in the temperature will be more if the work done is more. So in reversible process, the work done is more in expansion. Therefore, the temperature drop will be more. So the final temperature to which it will go, the system will be lower than the final temperature that the system will go in an irreversible expansion which has consumed less amount of work. Is there any iota of doubt again, Miss Sami?
No, sir.
And now tell me, you know, this is a different situation that we discussed before, that when you start at a particular point and we carry out an isobaric process. That was a different situation where we were saying that we start from this constant pressure. The same constant pressure, the work is done. This is isobaric, this is isothermal, and this is adiabatic, and this is isochoric. So that discussion was not this one. This one, the external pressure is this. But there, the external pressure was the starting point. Each process will start from the same initial pressure. In this case, pressure will remain constant. In these three cases, the pressure will change. And in this case, volume will remain constant. And in these two cases, three cases, the volume will also change. So these are very fascinating things. And if you are not uh, giving some time, because I am just dumping, I think the word which will be you will be preferring is a dumping, but I am not doing that. I am disseminating my experience. But it might appear to you that I am dumping my experience to you, and you think that you can be able to assimilate and realize, visualize without proper revision. No, it's not possible. Not only revision, but also to solve problems. So that situation, we said the isobaric work done is more, because you started from the same pressure. The work done in isobaric process is more, followed by isothermal, followed by adiabatic, followed by isochoric, which involves no work, only change in pressure uh, against change in temperature, Amundsen's law. You understand? So this is Boyle's law. This is Charles' law. This is Amundsen's law. But this adiabatic, which excites me to a large extent, is adiabatic gas laws. Gamma comes in for the ideal behavior. To have a reversible process, you don't use Boyle's law, Charles' law, you have your own set of laws for reversible process for this particular graph. But when it is expanded or compressed, from when it is a compression, then the pressure, the final pressure under which it is compressing, the higher pressure, in that case this one, with which it is compressing down, that will be taken as P external. In that case, the amount of work done during adiabatic irreversible compression, I am talking of compression, will be more than the adiabatic reversible compression, because it will go in the same direction, because it is all infinitesimally slowly. This case, we coin the term reversible with isothermal reversible, but this is only reversible but not isothermal. Temperature is changing continuously. As more and more work is being spent out from its own body, the body becomes cooler and cooler. You understand? If I go on explaining uh, uh, in, 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 in with a more and more visualization and example, then it will take long time. I'm doing that so that you can have a visualization of the principles in your system. But for that, you have to solve problems. Now, I have another follow-up question. And now I was thinking of, I have a follow-up question is, supposing we start, this is the PV diagram, start from this point and carry out compression. Says 20 liter to 10 liter backward. Then supposing I say these are the graphs, start from the same point. Tell me which one is which. Obviously, there will be no iota of doubt this will be isobaric process. This is a compression process. And this is isochoric process. There is no compression. This is only, you know, heating process or cooling process. This is isochoric. So pressure is increasing, temperature is increasing, so that P and T variables will be there. And between these two, which one is which? Who can tell me? That's what I was talking of when I was talking of there is a which one?
Sir,
Supposing I
sir,
will call it as 1, 2, 3, 4. These are the 4 curves. So 2 and 3. Between 2 and 3, which one is adia? Which one is isothermal? I have already told you. I have already told you are unable to recapitulate.
the
So
And
2
isothermal will,
3 is
yes,
adiabatic.
Omkar.
sir, 2
First,
will be
Omkar.
isothermal, sir, 2 will be isothermal.
And 3 obviously will be adiabatic.
Yes,
Sami,
sir.
you wanted to tell something?
That 2 is isothermal and 3 is adiabatic.
Rudra?
Sir, 3 is isothermal and 2 is adiabatic.
Precisely, 2 is adiabatic. Just the opposite. I told you.
It is compression, so
It is compression. You are going in this direction. So, this is isothermal. I told you in one problem, I told you that the isothermal is going below. Why? Now the question arises why? Then we shall compare this. These are all reversible. This is reversible. This is reversible. But this is isothermal. This is adiabatic. The difference is there is a change in temperature. So there is no change in temperature in the isothermal. Why the adiabatic uh, curve for the compression process runs above the isothermal process? Yes. Now I taught you the gaseous state chapter in greater details only because in thermodynamics we will be dealing gaseous state, particularly in the heat engine we'll be dealing with the gaseous state. Tell me why? Either you can take a constant volume and compare why the pressure of isothermal is less than adiabatic, or you can take a constant pressure and say why the adiabatic volume is more than the isothermal volume. I have given you a clue for me to answer. Yes.
Sir, in isothermal temperature is fixed,
Mhm.
but here the T is in adiabatic it is more.
In
That's right.
adiabatic what?
The
Adiabatic what?
temperature is
Huh?
irreversible.
No. This is not irreversible. Both are reversible. Had
Sir,
it
in
been,
adiabatic temperature is increasing.
yes, Rudra is correct. And you also were correct, Omkar, that during compression, the temperature increases. Why? Because the work is done on the system. As a result, the whatever work is done on the system is stored as internal energy. So the internal energy increases, and so temperature increases. So because temperature is more, because in isothermal temperature is less, so for a fixed volume, supposing volume is fixed, the temperature is less, so the pressure is less. And here the temperature is more, the volume is more. This is Charles' law. It can be used to explain why the corresponding points of isothermal compression lie lower than the corresponding points in the adiabatic expansion. Both are reversible, mind you. We are not using the term reversible in adiabatic, but we should coin the term adiabatic reversible compression, and this is isothermal, always is coined with reversible, right? So, or if you keep the pressure constant, then you will find as the temperature is more, the volume uh, is more, and constant volume. So Hamilton's law, I'm so sorry. We are keeping the volume constant. As the temperature is more, the pressure is more. Because in adiabatic temperature is more, we have kept the volume fixed, this point and this point, kept the volume fixed. So as the temperature is more, the pressure is more. Here temperature is less, pressure is less. That is Hamilton's law. And if you keep the pressure constant and compare these 2 points, you will find as the temperature is more, volume of the adiabatic case is more than the corresponding volume of isothermal case. So either you can apply Hamilton's law or Charles' law to prove that the isothermal curve during compression runs below the adiabatic curve. This is compression. But in expansion, you already know, we have discussed several times, start from a point. Here is this is the isothermal, supposing expansion, and this will be the adiabatic expansion. Of course, this is the isochoric, cooling. and this is isobaric expansion. So in that case, the isobaric work done is maximum, followed by isothermal, then adiabatic, and no work done for isochoric. But during compression, tell me the order which involves the highest energy. I mean, so work done. What is
Sir,
the order?
sir, isobaric is greatest, then isothermal, then adiabatic, then
No. Compression.
sir, order of compression.
Huh.
Sir, in compression, isochoric is zero.
No. Tell
Then
me in the decreasing order. Tell me in the decreasing order.
sir, in decreasing order, it is adiabatic is highest, then isothermal, then isobaric, then isochoric.
Yes. But during expansion, what is the order?
Sir, it is isobaric is greatest, then isothermal, then adiabatic, then isochoric.
Isochoric, we really we feel very pathetic because no work is done. We are putting it in the fray, in the competition. So isochoric doesn't involve any expansion compression work. So, and now come to this point. When you are compressing under external pressure, supposing the final pressure is this. So this is not the isobaric. I mean, this is not the the work done during irreversible. Uh, this is gone and this is gone. This is adiabatic. This is adiabatic compression, and we are coming to the final pressure. This one, and from here to here, we started from 20 liter. So this area will be the work done during adiabatic compression in an irreversible manner, because the fixed external pressure is the final pressure under which it is compressing. Under its shoulder, a big 20 kg load is there. I mean, high load is there. It's compressing under that higher external pressure. So the area bound by this big rectangle is much greater than the area bound by the same graph, reversible adiabatic graph, expansion, compression follows the same because it is reversible, goes infinitesimally slowly. I hope you understand. Raise your hands who have understood. Because we are not going anyway further today in our agenda, in our plan. We are at the old position. Yes. So the problem that we are doing, I am more keen to solve problems. So the final temperature that we found out was,
So 259.3.
yeah, it is 259 point, yes, 259.3, and that will be used here to find del S. Del S that we are finding out in the irreversible. We have not yet come to the reversible. Del S irreversible. Uh, just tell me in a broad-based manner whether del S will be 0 or will be positive or negative, and what about the del S of the surrounding in an irreversible adiabatic process. Here we are dealing with expansion, maybe sometimes compression. Here in this problem we are talking of expansion, but we discussed all varieties of possibilities like compression also we discussed. Now, if I ask another follow-up question to Sami, now from 20 liter to 10 liter compression has happened adiabatically, reversibly, and adiabatically, irreversibly. The final undoubtedly temperature will be increased. So which temperature will be higher? A reversible temperature will be higher, or the irreversible compression temperature will be higher?
The irreversible compression.
Precisely. Work done in the irreversible compression is more, and the reversible compression is less. So it will generate more internal energy because the work is done on the system, in this case in compression. So the temperature increase will be more. The final temperature in compression is more in irreversible compression than in reversible compression. Now here we are dealing with expansion. So del S টা कौन होगा? Whether it will be positive or it will be zero or negative or what? You are not revising anything. Yes, Rudra?
Sir,
Yes, Omkar?
sir, del S or surrounding will be 0.
And what about system that we are going to find out?
So it will have some positive value.
Precisely. In any irreversible process, as we have learned in second law, in terms of entropy change, the change in entropy of the universe will be positive, will be greater than zero. Since Omkar has already said that surrounding has nothing to do because it is completely insulated from the system. So del S surrounding will be zero. So definitely del S system has to be greater than zero. Otherwise, the second law will be proved to be wrong. Nobody so far has proved the second law to be wrong. Therefore, irreversible process which is fast, FAST, has to deal with the increase in the net and entropy of the universe. So system is zero. So this surrounding will be zero. There will be no calculation, nothing. But now we are going to find out what is del S of the system, which has to be positive. Now let us try to establish that in our calculation. Calculate del S. Now we have got everything, that is 2.303 into N is 1 mole. Then CV. CV is 3 by 2 into 3 by 2 into 8.3. This we will be separating by a line into log T2 by T1. T2 is 259.3, the cooling temperature finally, and started with T2 by T1 is 300 plus 2.303, or if you have ln in your this thing, so you may not write 2.303, straight away go for ln, it will be there. So n is 1, 2.303 n into r is 8.3 log V2 by V1. V2 is 20, V1 is 10. Now you find out, undoubtedly this will be negative, this will be positive, and definitely positive will have a will will weigh out, will be
Sir,
numerically greater. Yes,
sir, 3.938.
say plus or minus,
Sir,
tell me.
plus, sir,
Yes, 3.
938.
This many joules per Kelvin. Because 1 mole is given, so there is no right to per mole, because 2 moles bhi diya jai parthanta, so it is joules per Kelvin. So you realized that in an irreversible process, there has to be an increase in the entropy of the system, because surrounding will have no change in entropy. In the reversible process, you will see that these two terms will cancel each other and del S system will be 0. So also del S surrounding will be 0, both, because the temperature drop in this case, in case of what? In the case of um, um, you know, uh, a reversible expansion, the temperature drop will be more. So much so that the whatever excess was there in this term will be not there. It will be exactly same, and they will cancel. We are talking of expansion here. This 259.3, you will find the final temperature will be lower than that as gamma minus 1 will come. Let us try to find out. This is over. In this problem, this adiabatic, adiabatic irreversible, we have found out del u, del u, del u is same as NCVDT. Del u we have not find out. Del u is NCVDT. N is 1, 3 by 2 into 8.3, and no, no. Del u we have not find out. Oh yes, W is equal to, yes, this is also del u. Yes, let us, you will find same answer will be same. If you use the temperature data that we have found out, the answer will be exactly 506.5 because you have found out basing on that P delta V minus P delta V. So if you use the same temperature and find CV delta T, the answer will be same. But let us go for, there is no space, what to do, find out for the reversible process. This is T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1, and the initial temperature is 300, volume was 10. Since it is monoatomic, 1.67 minus 1, it is 0.67 is equal to T2. We are going to find out V2 is 10. So this is 20, I'm sorry. The initial volume was 20 to the power 0.67, and the final, oh no, 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 no. So it is expansion, 10 to 20. And the final volume is 20. Am I correct?
Yes, sir.
So you find out what is T2. The adiabatic gas laws are applicable for reversible process, not for
Sir,
irreversible.
188.55.
So T2 you are getting 188.5 Kelvin. Now see how much lower than this. It was 259. It was 259, Sami, and others who are watching directly from the YouTube. It was so high. 300 initial dropped down to 259.3 in irreversible because it is the small rectangle, and in reversible, which is the total area bound by the graph, it is more. So the temperature drop is more, and the final temperature that we found is 188.5. Now we can find del u is equal to NCV delta T, that is 1 into 3 by 2 into 8.3. This time delta T is the final temperature is 188.5 minus 300. So has to be negative because expansion work, there is a decrease in internal energy, and there is a negative work, and hence negative internal energy change. So what is the internal energy change?
Sir, minus 1388.17.
Now you see the internal energy change in irreversible process was so small. It was only 500 something. If I remember, it was 800. It was 506 only, because it is small rectangle and this one. And in the case of reversible adiabatic expansion, it is some 1388. Are you cross checking, Mr. Both of you calculate. Don't leave that someone is doing and I will be free. No, you must do calculation. Then only you get a feel. And what about del S system, Sami?
Sir,
Sami, what will be in a reversible process? What will be the entropy change of the system? Okay, okay, you are not able to catch it. Omkar,
sir, 0.
and what is the entropy change of the system? Surrounding.
So that is also 0. It will
That is
cancel out.
also 0. Hence, del S of the universe is also equal to 0. And you can testify that. You can yourself check uh, system by using the same, you know, equation, that is 2.303 into 1 into CV, that is 3 by 2 into 8.3 log T2 by T1. This time T2 is 188.5 by 300 plus 2.303 into 1 plus R into log V2 by V1. You will find these two terms, this is negative, this is positive, they will exactly cancel it, it will come to be 0. That's the beauty. Samita, did you understand?
Yes, sir.
Well, I understand, I appreciate, I understand that you have understood. But the thing is that you are not able to, these things are so, I can't say hard, so intriguing for you because you are a beginner. These are, making your mind very puzzled sometimes, very these things. But do try to revise again and again if you have time. If you don't have time, then you read it mechanically. I don't mind, because many people, they study this chapter completely mechanically, completely mechanically, without understanding what is going on. And, and as far as your NCRT book goes, so much of things are not perhaps there. You can have a look. We will have a look at the end of our program, this chapter thermodynamics. To what
Sir,
extent? Uh,
sir,
yeah,
it is not coming 0.
is coming. It will be very close to
Here.
0.
Yes, sir.
So there must be, we are having some a human a human calculation error. Tell me how much you are getting.
Sir, 0.099.
Oh, that, a guy like you should not have questioned this one. We have enough human error. We are not taking 3 places of decimal, or maybe 10 places of decimal. So it has to be 0. There is no way out. In all the calculation, all the data that you are taking, we are taking, we are taking only the first place of the decimal. We are not taking at least even the third place of decimal. Significant digits we are not using. Had we used that, it would have been even. How much you got? 0 point.
Sir, 0.09.
Had you taken 3 significant digits after decimal point in all the data, then you would have got 0.00 something. Then is it not same as 0?
Yes, sir.
So
Yes, sir.
this question, at least Rudra, you should not have asked. You are such an intelligent guy. Anyway, to err is human, and to rectify is human. Um, okay, that we have finished. I think this other two which are pending with you, this one, this is a cyclic process. You do it at home, which Mr. Omkar says he has done. Have you done?
Yes, sir. Yes, sir.
And what about this one? No, this one we are doing. Now, what is this one?
So this one, I think this one we have done, which you were, yes, sir, this one we had done, sir.
You have
Last
done.
class. Yeah, no, sir, last class you had only done, sir.
Yeah. Yes, yes. No, 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 no. This is a new question I am giving you. This is a new question which I have put yesterday. You do it at home, right? It's a simple one. Now see, I'm showing you the graph, PB graph. 10 liter, 2 atmosphere pressure. This is 2 atmosphere pressure is expanded isobarically. It was 10 liter, 10 and 2 atmosphere isobarically. And to state 2, this is state 1, this is state 2, and the volume gets doubled, it becomes 20 liters. And then the volume, now it is expanded isothermally and reversibly. It is expanded isothermally and reversibly to state 3, and then cooled isochorically to state 4. And the final temperature is 200 K. Finally, the gas was compressed adiabatically, and this we have done, I think. Yes, yes,
You say yesterday only we had done this.
yes, we have done it. Sorry. Another problem is somewhere, I think you'll find in another. Okay. Now, without further delay, let us try to complete today's program, and then we'll be back to some of the numericals. There are umpteen number of numericals that you can be excited. Acha, this question have you done in the thermodynamics of equilibrium? I had given. No, this one you are not supposed to graph. I have given, but Rudra, you are trying to dodge this, that I have not given anything related to graph. The
So,
equilibrium.
sir, not this one, sir. I have done some other two questions you have given.
This question I had not given. I have not told, right?
No, sir.
Okay. Then which questions I had given?
Sir, it was from another file.
This file? Oh, yeah, yeah, this file. This one.
Sir, in this one, sir, I am getting some different answer in the second question. Yes,
This
sir.
one.
Mm, sir, I have done this, and the second one I'm getting some different answer.
This one.
Sir,
This one.
SP5. Yes, sir.
Different answer.
Yes, sir.
Let us see. Determine del G under standard conditions using standard free energy of formation from the table for the following. So now the tables are different. What you are taken, what values of del G formation you have taken, from which table you have taken.
Sir, the blue one.
This one. HCN it is given 105. In some other table,
Yes, sir. I have taken N2 from that.
it is
Yes, sir. From
105. This
yes,
is
sir.
121, sorry, 121, because you have to use the free energy of formation directly. This one and 121. I think you have taken 105. For that, del S data will be, you have to use the del S data. Have you
Yes,
used the S data?
yes, sir. I have used both.
That means directly from del G F and also using the Helmholtz equation, both.
Yes, sir.
Why? Why you spend so much of time? Let's see 121. And you try to just see which other data required here. We need SCN, O2 is 0, water G is how much? This is 121.
Sir, minus 237.2.
And del GF water G is equal to how much?
Sir, minus 237.2.
And CO2?
Sir, minus 394.4.
And this is 0. Elements,
Yes,
del
sir.
H,
Both
del
are zero.
HF is 0 and del GF is also 0. Are you telling del GF or del HF?
Sir, del GF.
Are you sure?
Yes, sir.
And let me check at least for water. Water, it is water gas, this one. This is minus 228.6. How much you have told me?
Sir, minus 237. Oh, sir, it is different.
Data are different, So the
Sorry, sir, I
data,
have taken in liquids by
no,
mistake.
liquid is different. Liquid, del HF is different, del G F is different. To kete कहली 228 point. ତମର memory ବି ଗଲାଣି 228.6. And carbon dioxide is how much? Is minus, this is okay, 394.4. This is 2. You know, we will not be sweeping any topic. I tell you the concepts and go. No, we have to apply them. Until and unless we apply them, we are not convinced what concept we learned. Meaningless. 0.6. Right? Then let us find out what is the free energy change, standard free energy change for this reaction. So standard free energy change of this, R stands for reaction, is equal to right minus left. So 2 into, this is water is minus 228.6 because there are 2 moles and these are per mole basis, plus 5 into 0. That means this term, 4 plus 4 into carbon dioxide is minus 394.4 plus this is 0. This minus the reactants, 4 into FCN is 121 plus 121 plus 0. So what is the result? Tell me.
Sir, minus 2518.
Minus 25.
Point,
What?
18.8.
So this many joules is the standard free energy change of the whole reaction, from which we can say this is spontaneous. Yes or no?
Yes,
It
sir.
is spontaneous, right favored, product favored, and you will find that the equilibrium constant will be coming 10 to the power plus something. So let us find out that. Predict the reaction spontaneous in the standard state? Yes. In the standard state, it is spontaneous. Find the equilibrium constant Kp. So what expression you'll be using? Are you directly using
Sir,
ln or log?
sir, long.
Ln, okay. Then ln Kp is equal to what? Tell me, what is the formula?
Sir, minus del G naught upon minus RT. Sir, upon RT.
Hmm?
Sir, the formula was
No, no, no,
delta
no,
G
no,
naught
no, no, I'm
equal
so
to
sorry. I'm so
minus
sorry. I'm so sorry. সেগুড়াকো দরকার নেই বাবা. Del G naught is equal to,
minus RT ln K.
yes, minus RT ln Kp. Because here the gases are there, so by default it is Kp. So since you can directly find ln, there is no problem. Del G naught you have find out to 2500 18.8 is equal to minus 8.3 into temperature is standard state. Standard state is 298, and Kp you have to find out ln Kp. Then you have to take the anti-ln, or else you want to make it log. Can you find anti-ln?
Sir, I am using calculator, so I can.
Okay, do that. Better that you for the general purpose, because log data will be given in your question. Log Kp you multiply by 2.303. Anyway, you tell me the answer. What is log Kp? And then antilog of that will give you what is Kp. Finally, tell me Kp. Because these things are so common, this calculation part, you should be very, very thorough. I mean, prompt instead. It will be quite high. It will be quite high looking to the value. But my value is coming 1568, right? But we
Sir,
have got,
I am getting KP 2.76.
Yes, sir.
So
Yes, sir. It's coming quite.
no,
2.76, sir.
we are doing a mistake. We are doing, these are all kilojoules. You find all these are kilojoules. So this has to be kilojoules. And there will be a factor 10 to the power 3 here. You understood what I am saying?
Yes, sir, we have taken in joules.
Now look to the value in the data table. You will find these are all in kilojoules. In the top part, you will find the data table is in terms of kilojoules. Are you seeing that? These are all in kilojoules per mole. So what you have got, which didn't match with my answer, I have to see. Not my answer. From the source I collected, it was given 1568 kilojoules, but we have got 2518 kilojoules. This is kilojoules. So multiply 10 to the power 3 and get me the answer. Then I will at home, I mean not at home, and later time when the class is over, I will check why it didn't match. This is 2 into minus 2 plus 4 into minus 10 over 4, and this is 4 121. This has to be this. This plus There minus, this is plus. No, answer is wrong. Because HCN nowhere the data is only in one table, not in multiple tables. I find the data.
Sir, it is uh sir, it is here, sir.
Yes. How much? How much?
Sir, I
KP.
can.
Hmm? You can't tell. Are you kidding me?
Sir, it is showing calculation outside the range. It's coming too large.
Yes, sir. Extreme
Now
length.
you tell me log
Like
KP how much? Forget about log KP how much?
the 442 point something.
Yes, sir. Yes, sir. 442.04.
442.04.
04.
So obviously KP is equal to 10 to the power 442. I really wonder how this is coming so high. 10 to the power 442. Forget about the decimal part. 442.
Yes.
Anyway,
Yes.
doesn't matter. This is the way how you calculate. Maybe somewhere some calculation might be wrong. You check again. This is ln RT. R is this temperature is 298 and this is P and this is Hughes. This particularly this is Hughes. Okay, I will check. But this is the correct process of calculation. I think there is some, uh, and supposing the calculation is correct, what information you get from here? That the reaction is 101%. To be in a lighter vein, we will say the reaction is 101% complete. If it is, now we shall study in equilibrium. If it is 10 to the power 10, then it is 99.9% complete. 10 to the power 15, 16, it is 99.9999% complete. So at 10 to the power 442, you check again. So it has to be 101% complete. Okay, you understood?
Yes, sir.
Yes, sir.
Okay, don't worry. Today we may not, since today is a today's Teachers' Day, an auspicious day, was we uh, remember and worship the teacher of teachers, who is the Almighty, the nature that I consider. This is not the so-called teachers. It is the day for the worshipping of the teacher of all teachers, is the nature itself, or as some of us call Almighty God. Um, we take up a simple thing today, is the Carnot cycle. It's very simple thing, and I'll give you the task of writing at home. Now this is simply a cyclic process. We have done so many problems on cyclic process that it needs no spending of time in our class. Now see this original initial Carnot cycle. Subsequently, it was modified to a large extent, but original Carnot was the person instrumental in giving the concept of internal combustion engine, where he devised 4 steps to make a cycle. The first step, supposing we start from A or start from B. Matter of fact, let us start from B. B to C is isothermal, reversible, expansion from a lower volume to a higher volume, B to C. Then again expansion, but this expansion is adiabatic. C to D is adiabatic expansion from volume V to volume V2 to V3. This is from V1 to V2. This is from V2 to V3. And then again isothermal compression at a lower temperature, because from V2 to V3 there is a cooling effect. So temperature has been lowered from T1 to T2. T1 is the temperature of the source, the hot source from which the system will absorb the heat energy. Heat energy, supposing Q1 amount of energy is absorbed by the system from hot source, which is at temperature T1. So, and it goes to temperature T2, which is called the cold sink, where some amount of heat it will throw. It cannot consume all Q1 amount of heat to perform work. So this is another alternative definition of second law, that all heat that is being absorbed from the source, from the hot source, cannot be completely converted to work, expansion compression work. Some part of it has to be thrown to another cold body, that is called the sink. So that it throws, and this is this D to A is isothermal compression, and then A to B is once again adiabatic compression. So two expansions, B to C, C to D, and two compressions, D to A to B. Ultimately you land at the same point. So in cyclic process, if you are carrying out I told you, if you are carrying out uh, reversibly, particularly you are to be careful in isothermal process, has to be slow, because the thermostat is maintaining the temperature. You have to be slow, but if you are not slow, you are doing the fast, it is irreversible, then the entropy change of the system will be less than zero, not like a single step where entropy change of the system will be greater than zero, as we have seen uh, visualized in solving a problem. But in a cyclic process, if it is irreversible, then delta S system will be less than zero, but delta S surrounding will be greater than zero. So the increase in entropy will be greater compared to the decrease in entropy of the system. The increase in entropy of the surrounding will be greater than the increase than the decrease in the entropy of the system, so that the net entropy change of the universe, that is system and surrounding, will be greater than zero. That we shall see. It's very interesting. Now let us take and the net process, since it is cyclic process, there will be no change in internal energy, daily will be equal to zero. So whatever net heat will be absorbed, some amount of heat is thrown, some amount of heat is taken, and this difference between this is totally used up in performing expansion work. Net, there will be expansion, because there is negative, Q is absorbed, means it will perform expansion work. Now let's go step by step. First, I have deliberately taken the BC step. Now these are the components which have been very represented in a very simplified manner. This is the system containing gas, and here all the sides are adiabatic walls, insulators, but the lower part is a dithermic wall to exchange heat. And this is this hot source at a higher temperature T1, and this is the cold sink at a lower temperature T2, and this is an insulating stand. When the system will be standing on this insulating stand, the all the sides will be insulated, and it will be really performing an adiabatic process. Now in the first step, let us take this system and put the dithermic wall, the lower wall, on the source, which is also dithermic, right? So it will absorb Q1 amount of heat during the process and it will expand. We shall find out what is the heat absorbed and what is the work done. And then the next step, we remove this expanded cylinder to keep it on the insulating stand, and it will further expand adiabatically because there is no heat exchange. The whole system is adiabatic now. Whole system is insulated now. So again, some expansion will happen adiabatically, and there Q is 0, and you can find out the net internal energy change is equal to work done, that is C N CV delta T. We can find out. Then next step is to, by that process it will acquire T2 because of adiabatic expansion. The temperature will be lowered and it will become T2. And once it becomes T2, put it under over a thermally conducting sink at lower temperature T2, and there you compress it. The compression will carry out under isothermal condition, an isothermal T2 condition. That same T2 here, T1 condition isothermal expansion, and in the T2 condition you continue to compress it till the volume becomes V4, and volume becomes V4. Then again bring it to the insulating stand and further compress it to come to the initial state V2, V2, V3, V1. What we have seen, this is V1, sorry. B is V1, then V2, V3, V4. So you come to the original volume V1. During this adiabatic compression, again temperature has risen, increased from T2 to T1. So we have to find out in each step, step 1 isothermal, we have put the system over this hot source T1. It is absorbing Q1 amount of heat from, I have written here small Q1 amount of heat from the source, and that is exactly equal to the work, expansion work, and that is minus, and minus becomes plus because Q is plus. So minus W1 will be also equal to plus RT1 ln V2 by V1. So you have completed the BC step, expansion from volume V1 to volume V2. V2 by V1, the minus is over because this is Q. A W is, only W is minus. So minus minus has become plus. This is Q or minus W, right? Then let us go to the second step. Second step is adiabatic expansion, CD from V2 to V3. So here del U, let us write down U every time we are changing. It's not possible. Okay, del U is equal to W2, that is CV T2 minus T1. Then let us go to step 3, DA, isothermal compression. So Q2 that that it will throw to the sink is the compression work. W is minus, so minus minus becomes plus. So Q2 will be negative. The work will be plus. Q2 will be negative because it will be throwing out. Because W3 is plus, there is a minus sign. W3 compression is plus, there is a minus sign. So Q2 will be obviously negative. V4 is less than V3. So this ln part will be negative. So Q2 will be negative because Q has been thrown out, evolved, right? So this is isothermal compression. Then adiabatic compression, that is delta E is W4, CV T1 minus T2. Then what we will be doing, we will be taking the total heat, net heat. The Q1 is plus and Q2 is minus. Obviously, I have written plus, but on calculation, the second term will be negative. I have written here Q1 is positive, Q2 is negative. So automatically it will come. And the net work done, you will find W1 he will find, now we'll be doing later, from the two adiabats, if you apply to point B and point A in this adiabat, and then point C and point D in this adiabat, you apply the adiabatic gas laws. T2, you are applying T2 from here, A, point A. T2 V4 gamma minus 1 is equal to T1 V1 gamma minus 1. This is adiabat AB, and adiabat CD, T2 V3 gamma minus 1 is equal to T1 V2 gamma minus 1. And if you take the ratio, you will find V2 by V1 is same as V3 by V4. This we get from the two adiabats. Now, when you write this V4 by V3, just to interchange, take V3 to the numerator, V4 to the denominator, so plus will be minus here, and in place of V3 by V4, you write V2 by V1. So we in both the terms you have V2 by V1. Take it common. R ln V2 by V1 is common, so T1 minus T2 is the net heat absorbed. Q1 is positive, Q2 is negative, and in terms of this, it is plus R ln V2 by V1 into T1 minus T2. Now, Q1 by Q2, if you take the ratio, Q1 by Q2, this is Q1, this is Q2, and you will find this ln V2 by V1 will cancel, RR will cancel, it will be T1 by T2. And if you crisscross, Q1 by T1 is equal to minus Q2 by T2. Here actually the concept of entropy was first came to the mind of Carnot in this particular step, that Q1 by T1 is remaining constant. Here, when it was absorbing Q1 amount of heat from the source and the temperature was T1 at the source, so the net gain in entropy, we already have known that Q by T is entropy. So the entropy change, not entropy change. So the entropy change by the system, that is increase of entropy that has happened while Q1 amount of heat was absorbed by the system, is exactly same the loss of entropy, the decrease in entropy that happens when Q2 amount of heat is thrown to the sink at a lower temperature T2. So these ratios are numerically same. So the entropy gain that happens during heat absorption by the system is exactly equal to the entropy loss that happens due to the heat throw to the sink. So in the net cycle, the heat change is zero. Whatever is being gained, same is being lost. So in the cyclic process, the system as a whole during a process, there is no change in entropy, and in the surrounding also there is no change in entropy. As much the surrounding is losing during the source, at the source, particularly we'll take source and sink as the surrounding for practical purposes. Whatever entropy the source is losing, same entropy the sink is gaining. So you also find the surrounding also involves no entropy change. So del S surrounding 0, del S system, you can call it system. I'm writing cycle, but you can write system is also 0. Hi guys who are watching from the YouTube source directly or will be watching later, we'll be stopping after this. Today we will not be so. Yesterday we became so desperate and so greedy to continue for almost 4 hours. Have you seen Miss Sami, the remaining portion that you left to join your family for dinner? No.
So I could watch only some portion of it, not
Okay,
the
okay,
full
okay.
part.
Okay, no problem. But during the, if it will be irreversible, as I have already told you, the situation will be different. I have written somewhere later. It will be irreversible, then there will be decrease, and whatever increase in entropy will happen during source to system absorption, more loss will happen at the sink. More comparatively, Q2 by T2 will be greater numerically. So the net decrease of entropy will happen inside the system during the cyclic process. But since the gain in entropy during the sink side is much greater, so the net entropy gain in the surrounding will be much, much greater than the net loss of entropy in the system. So if you add these two, the net entropy change of the universe will be positive. So we in no way we are going to refute or challenge or oppose the second law of thermodynamics. Now let us come to this part, which you will write step by step at in your copy, that if you add all the work terms W1, W2, W3, the W2 and W4 will cancel out, because this is CV T2, T2 minus T1, that is CV T1 minus T2. So it will cancel exactly the adiabatic work done during expansion is positive. The adiabatic compression is exactly same negative and same numerical value. So they cancel out. So the only the isothermal part is left out. And if you add them, you already you know this is the work done. A W1 is minus RT ln V2 by V1. W1 is minus R. So I have written here, very confident in your concept. While you are talking of W, it has to be minus. So minus RT ln V2 by V1, RT1 ln V2 by V1. And in W3, as you have seen here in W3, it is minus RT2 ln V4 by V3. Since V4 by V3 is minus, so since you have to interchange this, so minus will become plus. So it will be plus RT2 ln V2 by V1, because V3 by V4 is equal to V2 by V1, as we have already derived it from the adiabats. So plus, therefore I have written here plus R T2 ln V2 by V1. And since I have taken a minus sign as the common, then this has to be minus. So W net is equal to, and we have proved that in the cyclic process Q net was plus. Just before bit, we know Q net was plus. If you take a common here, this was plus R ln V2 by V1 T1 minus T2, and the work done will be minus R ln V2 by V1 T1 minus T2. So this is proved that in a cyclic process, net work done is the opposite of the heat change that has happened. Now, the efficiency of a Carnot engine eta is defined as the magnitude of the work done. Don't take the minus sign. The work done, this expansion work will be negative, but don't take that. The magnitude of the work done and divided by the heat absorbed from the source. So if you write net work done is this without taking the minus sign, only write R ln V2 by V1 into T1 minus T2, and Q1 is ln R ln R T1 ln V2 by V1. So R ln V2 by V1 will cancel out. Only you are left with, T1. T1 minus T2 will be left out in the upper side, in the work side, in the numerator, and T1 will be left out in the denominator because it is Q1. So the ln V2 by V1 R, they will be cancelled out. So eta will be equal to 1 minus T2 by T1. So the efficiency of even an ideal reversible Carnot engine cannot be equal to 1. It will be always less than 1. T2, maybe T2 is definitely less than 1, but this ratio is finite. So 1 minus a finite value will be definitely less than 1. Therefore, in all possible ideal cases, also the efficiency of Carnot engine cannot be 100%. That is also another consequence of second law. It is impossible. So second law is defined in another way. It is impossible to construct a cyclic engine that transforms all heat into work without surrendering all heat into work without surrendering some heat to the cold sink, cold reservoir, or called sink. So efficiency of a heat engine only depends on T1 and T2, the temperature of the source and temperature of the sink, because we learned it is 1 minus T2 by T1, not depending on any other thing, not on any other thing. So efficiency of Carnot cycle operating in irreversible condition is definitely less than that operating under ideal conditions. So this is a misnomer. This is a reality. You will find the efficiency will be further less. Whatever is the efficiency, 1 minus T2 by T1 is the efficiency when idealized. But the idealized means reversible. If it is irreversible, then it will be further less than that. That I have written here. In ideal, Q1 by T1 is equal to minus Q2 by T2. There is no change in system, either in the system or the surrounding. And therefore, if you integrate this this is the integral form, this is the total integral will be 0. Whatever heat. The first term is the gain in entropy. The second term is the loss in entropy. So the net will be 0 because in reversible process both are same. So the net change is 0 for the system. But the efficiency of irreversible process is less than 1 minus T2 by T1 because the total work done in the irreversible cyclic process is less than the reversible cyclic process. So the efficiency will be less. So dq by dt total integral will be less than 0. This is there is a decrease in entropy. This is the entropy of the system. The change of entropy in the system will be less than 0 because the efficiency is less than the efficiency of the idealized engine. But there will be much greater increase in the entropy of the surrounding. So the net entropy of the universe will increase. So this is another version of the second law. So in a cyclic process, the net integral of dq reversible by dt will be either less than 0 if it is irreversible, equal to 0 if it is reversible. Equal to is for reversible, less than 0 is for irreversible. This is irreversible, this is reversible. So this is another Clausius inequality, and that these are some of the examples that is of Carnot's engine, Carnot cycle that is operating in nature. In nature, hurricane, thunderstorm, these are approximate Carnot cycle, and these are the actual one. Steam engine has a radiator, this sink, where heat is thrown out to a sink. That sink contains water and ethylene glycol to lower the temperature in cold areas, that you will learn in your class 12. Power plants also has a cooling tower. So this finishes, and we have the same problems. Some of the problems have already worked out. Some of the problems, yeah, this is worked out. Yeah, yes, this was the question you have asked, right?
Sir,
So I think we will discuss this. This is a very interesting question. Before that, I will also discuss a TV graph. We have been acquainting ourselves with the PV graph, but in PV graph also we can show the different processes. For example, in this graph, process 1, process 2 is isothermal. Why? Because the temperature is constant. The volume is increasing means pressure is decreasing. So this straight line is representing an isothermal expansion process. This is a TV graph, not a PV graph. And 3 is an adiabatic expansion because both temperature and volume are changing. Temperature is decreasing, volume is increasing. So that is bound to be an adiabatic expansion. And this 4 is again temperature remaining constant, isothermal compression, where the volume is decreasing, pressure must be increasing, there is no doubt about it. And this is 1 is adiabatic compression. Once again, the volume is decreasing, temperature is increasing, so adiabatic compression. So a TV, this is also a TV graph. So in TV graph, you have to know, since here V1 and V1 are constant, these two are constant, so this is isochoric process. Since here T1 and T1 are constant, this is isothermal process. And B to C, P2, P2 are constant, this is isobaric process. Accordingly, you have to find out, and there is 4 choices. You try to work out and tally with the 4 choices. I think you have sent that question, right?
Yes, sir.
Yes, sir. These are the 4 choices. I have worked out the answer. A, QAC is equal to del UBC, and work done AB is equal to P2 V2 minus V1. You work out the details, you will find the correct answer will be B and C. I am sending, don't look to my answer, you yourself answer. You will find both B and C are the correct answers, others are wrong. So this is the end of our program. I think you have understood the Carnot cycle. Raise your hands, please, if you have understood thoroughly what I have said mathematically as well as conceptually. Oh, great. So my request is since we could not spend any time for writing, spend most time in calculation, you write down A to Z, all word by word that we have written in this file. Okay.
Okay, sir. Yes, sir.
Tomorrow
Okay, sir. Yes,
will be our last class on thermodynamics, where we'll be doing a lot of integration. I mean, not the mathematics of integration, but integrate the first law and second law and derive many other differential equations and other things. And then we will talk about, we'll discuss vividly about the thermodynamics of refrigeration, where another definition of second law will come up, and the opposite of that is heat pump. Not not the opposite. The opposite is Carnot cycle's opposite is refrigeration and heat. The difference between refrigeration and heat pump is the source and sink. If you make the source as your room and sink outside, then it will be refrigeration. But if you make your room as the sink, then it will be heat pump. In cold countries like in US, northern US, the refrigeration and heat pump, they go hand in hand. Just 2 switches, they will be, the moment it is acting on a refrigeration mode, then your room is converted, your entire house is converted to a source where heat is continuously being withdrawn, and it being work is done, because it is the opposite of Carnot cycle. Work will be done, the heat will be withdrawn from the cold source. Cold source will be called cold, and sink will be hot. It will be thrown to the hot sink, right, in the opposite. And if the source will be your room, whatever cold is there, it is cold, but whatever cold is there, it will be made further cold. And this the sink is outside your home, so you find that outside the uh, refrigerator or air conditioner, same. Air conditioner and refrigerator, same. Air conditioner is working under this refrigeration mode. So outside is the hot sink. But if you make the opposite, your room becomes the hot sink, where the cold body is outside. It will draw heat from outside, and during the process, some coolant will undergo expansion. Evaporation causes cooling, so it will draw the heat from the cold source from outside, and it will throw to your room as your hot sink. So because the temperature is low, it will make little more so that you feel warm, because outside temperature is low. So inside temperature should have been low, but because it is throwing heat to the room, acting as a hot sink, your room is getting heated. So we talk about that and how to find the performance coefficient. Just like here in Carnot cycle, we found the efficiency, that is called coefficient of performance in the reverse Carnot cycle, that works in, for refrigeration, that is for cooling effect for the room or for the refrigerator. and and we shall also look to some other aspects of entropy change. What happens to the entropy change while we stretch a rubber band and then unstretch it? It is just the opposite of what happens to a normal spring. I mean, uh, elastic string that we learn. This is called the entropy spring. Entropy spring. It's not a normal mechanical string that entropy changes. Entropy increases uh, while we stretch. The entropy increases, and when we unstretch, entropy decreases. That is a normal mechanical string. But in the entropy string rubber band, opposite happens. When we stretch a rubber band, the entropy decreases, and when we stretch it, entropy increases. Why it happens? Which process is endothermic? Which process is exothermic? All these details we shall discuss, and many more things next time. I mean tomorrow. Bye bye. Any question? Any other? Not related to study. Any other question you want? So guys who are watching from the YouTube, have a nice night. So happy Teachers Day once again. If you are an Indian, if you are non-Indian, then uh, very good day or night. And if you have enjoyed our program, our deliberation, is hit the like button. And if you have not subscribed, please consider for subscribing to our channel. Bye bye. Hello.
Yes, sir.
Yes, sir.